And now in this example, we are going to produce 300 million pounds per year of ethylene in a flow reactor, design of a full-scale tubular reactor. Determine the flow reactor volume necessary to produce 300 million pounds of ethylene a year from cracking a feed stream of pure ethane. The reaction is irreversible and follows an elementary rate law. We want to achieve 80% conversion of ethane, operating the reactor at temperature constant of 1100 K at a pressure of 6 atmospheres. So solution, here we have ethane that goes to ethylene plus hydrogen in a relation of one molecule of ethane goes to one of ethylene plus one of hydrogen. So let's say that A is ethane, B is ethylene, and C is hydrogen. So in symbol we will have that A goes to B plus C. So it's an increase in volume. Because we want the reader to be familiar with both metric units and English units, we will work some of the examples using English units. In this case, we are going to use some. The molar flow rate of ethylene exiting the reactor is FB equal 300 times to the 6th, which are the demand of the product per year. So 300 times to the 6 pounds per year is equal to 0.340 mole pounds per second. After we make all this change of units from years to days and then hours, seconds, and from pounds to mole pound. And next, we are going to calculate the molar feed rate of ethane FA0 to produce 0.340 mole pounds per second of ethylene when 80% conversion is achieved. So FV equal to FA0 times X, and FA0 is going to be then FV, which is 0.340 divided by 0.8 equal to 0.425 mole pounds per second, which is equal to 402 times to the 6 pounds per year. So here, from the necessity of the market, we come with the molar flow rate of the product, and from there we went to calculate the molar flow rate of the reactant. Now we come to the flow design equation. For the flow design equation, we had that from the molar balance that FA0 dx divided by dB equal to minus RA. Rearranging and integrating for the case of no pressure drop and isothermal operation, T equal constant and P equal constant, we will have that the volume is equal to FA0, the integral of dx divided by minus RA, with the limit 0 to x. And from the Rayleigh law is equal minus RA is equal KCA, because they said it was first order, with K equals 0.072 seconds to the minus 1 at 1000 K. The activation energy is 82 kilocalories per mole gram. From the stoichiometry for isothermal operation and negligible pressure drop, the concentration of ethane is calculated as follows: gas phase, constant temperature and pressure. B, the volume is equal to V0 times Ft divided by Ft0. is equal to V0 times 1 plus epsilon x, and the concentration of A, which is FA divided by the volumetric flow rate, that FA is equal to FA0 times 1 minus x, and B is equal to B0 times 1 plus epsilon x. At the end, we will have that Ci is equal to Ca0 times 1 minus x divided by 1 plus epsilon x, and C of C is equal to Ca0 times x divided by 1 plus epsilon x. Then we combine all these equations to come that the volume is equal to Fa0, the integral of dx divided by kCa0 times 1 minus x divided by 1 plus epsilon x. This is equal to Fa0, the integral of 1 plus epsilon x dx divided by kCa0. The integral of 1 plus epsilon x divided by 1 minus x is in the book and is at the end of this page. So the volume is equal to Fa0 divided by Ca0, the integral of 1 plus epsilon x dx divided by k times 1 minus x. So we bring all the constants outside of the integral, and we will have that the volume is equal to Fa0 divided by kCa0 and the integral of 1 plus epsilon x dx divided by 1 minus x. And that integral is equal to 1 plus epsilon natural log of 1 divided by 1 minus x, that minus all that minus epsilon x. So parameter evaluation. From the concentration of A at the entrance, CO0 is going to be the mole fraction Y0 times the total concentration CT0. So it's going to be the mole fraction times P0 divided by RT0. Remember that this comes from the law of the gases. So CH0 is going to be 1 because Y is only ethane that comes into the reactor times 6 atmosphere divided by 0.73 cubic feet atmospheres divided by mole pound grad Rankine times 1980 Rankine. So we will have that CH0 is equal to 0.00415 mole pounds per cubic feet. Epsilon is going to be Y0 times delta. Y0 is 1. Delta is 1 plus 1. Remember that is an increase. Minus 1 is equal to 1. So it's equal, epsilon is equal to 1. But the rate constant K, we have it at 1000, but we need it at 1500 K. So we come that the Arrhenius expression that K at temperature 2 is equal to K at temperature 1 exponential of E capital divided by R capital, which E capital is the activation energy and R is the constant of the gases, times 1 divided by T1, T minus 1 divided by T2. So remember that here the sinus minus signs of the in terms of the exponential becomes positive because we change the limits instead of saying instead of 1 divided by T2 minus 1 divided by T1, we put it the other way around and we change the sign. So this is going to be the K at the temperature T1 exponential of E divided by R times T2 minus T1 divided by T1 T2. So if we substitute all the values for these constants and parameters, at the end we will have that K at T2 is equal to 3.07 seconds to the minus 1. Substituting in the equation for volume all these values, we will have that the volume is equal to 0.425 mole pounds per second divided by 3.07, this is K, times 0.0415, which is the volumetric flow rate, and then the integral. At the end, we will have that the volume is equal to 80.7 cubic feet or 2.28 cubic meters. So this reactor can be built with a bank of 2-inch scheduled 80 pipes in parallel that with 40 feet long. For pipes scheduled 80, the cross-sectional area is 0.0205 square feet, and the number of pipes will be 98.4.